All right. So this is going to be really our third AI lesson if we count the prompt engineering. Um, what we've learned thus far is, we've learned about learning models and what they are, sort of in the bigger scope of machine learning. We've talked a lot of big picture stuff, and over the course of the next several days, we will build our own classification learning models. Tomorrow, we're going to look at a binary classification model. And if you all remember, we talked about how binary classification is really about taking a whole bunch of data, which could be pixels, right, that form an image of a cloud, and feeding it into something called a neural net. If I go ahead and we pull up our diagram here of all these nodes or neurons, and we learned how each of these is really going to be more or less sort of like a tensor, or a group of these will form a tensor, and some fancy statistics gets run to produce a probability. And that's our output, a number between 0 and 1, saying if this picture is a picture of a cloud or not. And then we tell the model if it's right or wrong. If the model is wrong, it will actually kind of move backwards through the net and adjust the weights and biases in the number crunching it does in each neuron to try and get a closer result. And we haven't gotten there yet. Today is going to be a bit dry, but we're kind of proceeding step by step, and we're going to see this over the next several days. And we learned about tensors, which is going to be our sort of building block for building this neural net. And today, and we also learned how to set up a Jupyter notebook and all the steps involved with that, and some pain points along the way as well. And then today, we're going to look at working with data. And we're going to cover a couple things in talking about data. We're going to talk about why data pre-processing is so important. In fact, it's really maybe one of the most essential parts of machine learning and learning models. We're going to talk about some common pre-processing techniques, specifically handling missing values. And we briefly touched on this talking about normalization at the end of the last lecture. We're going to look at a practical example with the water potability CSV data from the Kaggle site, which if I pull that up, we've kind of glanced at this, but we've seen this. It's this giant CSV file of water potability that has these attributes of pH and hardness and so on, that then eventually, if I can get this thing to scroll, well, I can't get it to scroll because of the annoyingness of the Chrome interface here. But all the way on the right here, there we go. Over here, we see this potability value, which is how drinkable the water is. And this is a number between 0 and 1. That's a prediction for a model based on each of these data sets. And we're actually going to work with that same water potability data today. And I've gone ahead and downloaded the CSV file, which is safe to say big. We have at least 1,000 lines here where each line is one data point. And we're not going to interact directly with them, but we're going to manipulate all of them. We're going to see how to use pandas to manipulate CSV data and do data pre-processing, excuse me. And pandas is a really popular library for scientific computing in Python, and PyTorch, in fact, uses it under the hood. And finally, we will actually end up splitting up our data into training and evaluation sets. So some of our data will be used to train the model. The other will be used to evaluate how well it does. and we're going to put it in tensors, which will set us up for tomorrow when we will start building a binary classification model. So remember, this training process happens hundreds or thousands of times, and each run, the model refines its predictability. So today is going to be a little dry because we are focusing still entirely on this sort of input stage right here. Right, where my inputs are, um, if we look over here at the water quality index, we've got pH, hardness, solids, chloramines, sulfate. And so we're processing that data, right? And our inputs here is going to be like, pH, hardness, chloramines, sulfate, and so on. And each of these forms its own input layer, right? With each of these as an attribute that then get fed into the model. So that's sort of the big picture for today. We will get our hands dirty with some code. Um, there's a lot to be reviewed here, right? Because a lot of this is conceptual. But again, the part that we're really focusing on today is getting the data into this funnel, right? So if I'm to add to this, what we're really doing here is some data preprocessing. And we'll talk about why we need to do that and why this is such an important step. But so this is today. And then tomorrow we will finally start looking at the funnel itself. Do folks have any questions about sort of the topics that we're covering today? And I know before we dive in, I know some of the feedback from the retro was around sort of like, how does this connect to the big picture? And that is a really good point. It is a little hard, I think, to illustrate. Where we're going to sort of end up is if we kind of look at this water potability example, we can actually see some some models that people have made for this using Jupyter notebooks, and this goes a bit beyond what we're going to learn because this gets a bit more advanced. But what you can see here is importing data, working with it. In fact, they start doing some data analysis to look at how well organized the data is, and we talk about normal distribution. And we can see here some of this data does not sort of fit a normal curve. And we'll talk about why we want data that we use to train these learning models to fit a normal curve. And so this person did a lot of data analysis and then use that essentially to tweak or process the data, right, to fit more of a normal curve. And this is more data science, and this goes well beyond what we're covering here. But just to sort of peek under the hood a bit to see, if we were building a model for the EPA so they could take water potability data from anywhere and feed it into our learning model and have a high degree of confidence that it would tell them if the water is drinkable or not, there might be data scientists on the team doing all of this work. And in fact, for real world machine learning, it is a bigger team. You often have data scientists and machine learning specialists working on this stage. You then might have DevOps people or software engineers work on, once the model is there, how do you put this model into other software so it can be used, right? So we might be working with an existing model and adding it to some sort of web app that scientists could upload their water potability data into. We might be working more closely with the machine learning specialists, maybe to optimize some of the training processes of the model or how it gets deployed onto the cloud, though that is a bit more DevOpsy. On a big team, we probably are not training the model ourselves, But if we're at a smaller company, maybe we are building an image classifier to see if people are uploading food or images of things they shouldn't be, or we're using a pre-existing model that we want to tweak and we need to understand if we can use it for this application or not. Um, so I realize that that's a bit broad, but to kind of step back, this whole model might just be part of one web app, right? If this will let me type, and that is way too small. I'll just stick with the big view here, where maybe we have a scientist using their browser to upload some CSV data to a web app. Maybe the CSV data needs to get saved to a database. Maybe the scientist needs to log into their account and it does all sorts of things. But then this web application eventually sends that data over to our already trained model for it to evaluate. I realize this diagram is a little off the cuff. Um, I hope this helps illustrate maybe just a little bit how the things that we're learning about learning models are parts of bigger systems. Does that make sense? And does that help a little bit to kind of paint that bigger picture? Okay, awesome. And the reality is, everything this week is going to be kind of separate from the rest of the course, um, in part because this is all newer in the curriculum, um, and in part because, you know, I would love to have us using learning models in our full stack applications. If we go down that road for future curriculum updates, we also need to do it in a way that doesn't overload everyone because there's already a lot of stuff to learn. So again, really think of this as like learning some fundamental building blocks and peeking under the hood of this really key technology. All right. Um, do folks have any questions before we dive in?
If we're following along in the curriculum, um, on the week three, like the AI
Oh yeah.
LLMs, what folder are we in? Are we in like one, two, three, four, five?
Oh yeah. Thank you for touching on that. I'll get our Google curriculum updated today. There's a little tweak here. I've actually jumped to section 3. We're doing 3 working with data today. Tomorrow we'll do 2. We need to flip the order of this, and then we'll get back on track.
All right, thank you.
Yeah, absolutely. I meant to mention that, and I got a little lost in the sauce. So thank you for asking, Chase. Yeah. So just to reiterate, today is lesson 3, working with data. Tomorrow we'll look at binary models, and then we'll move on to training learning models, optimization, and so on. And let me just pull up my notes here real quick. And give me 1 second here, folks. Oh, did I stop my share?
No, you good.
Okay, thank you.
We're looking at your desktop now.
Got it. Okay, give me 1 sec here to grab the window that I want. Um, all right, thank you, James. Okay, so why do we want to pre-process data? So there's a couple
You
big
need to,
problems.
sorry, go ahead.
Oh, what's up?
I was going to say you need
Oh,
to eliminate things like outliers and put it in a format that is actually useful for processing instead of just a bunch of garbled nonsense.
yeah, exactly. We need to eliminate outliers. Like what's an outlier?
In the data, the extreme cases that are like one-off could be just environmental factors that happen on that day of collection or something like that. That's just not the norm and it's going to skew your data.
Yeah, exactly. Exactly. And then you mentioned we need to get the data like in a consistent format.
Yeah.
Totally. And also, though this is a bit out of scope of today, um, normalizing or scaling our data can improve model performance. One of the biggest outliers is like a null value, an empty data point. And if I hop over here to the water potability CSV, I think we can actually see a couple examples of this here in the data. Let's see, here we go. So if y'all can see, and I'll pull up the annotator tool. So where my pointer is right now, if y'all can see, so here's a null data point, here's a null data point, right? Um, one's over here as well, one's over here as well. And so the problem with these is that just having empty data points will mess up our training model. Um, I'm not sure if it would throw an error, but it definitely would give it not very useful data that would make things worse. So we actually need to replace our null data points, or rather, we need to handle them in some fashion. And there's a couple different ways we can do this. One is removal. We could delete rows or columns with missing values. Another is essentially we could replace missing values with, say, the average value, such as maybe the mean. There's also, and this is called, so I really have not seen this word used in other contexts, imputation. There's also interpolation, which I have seen, which is estimating missing values based on other data points. Right? And these are some of the strategies for dealing with missing values in null data points. And just to start, and the strategies that we're going to look at today, we're not going to deal with removal because as we're going to see in a little bit, once we start working with this data in Jupyter notebooks. But if I can kind of see this just by scrolling through this, look how many missing data points are here under pH. If I just start getting rid of all of these, then all of a sudden in my pH column, I have less data than the other columns, and that's going to make my data harder to work with and harder to pass into the model. I may not be able to at all. It would also mean a whole lot of rows of data would get eliminated. So in this case, just getting rid of rows or our missing columns of data is not a very useful strategy. And we're instead going to look at either replacing these missing values with an average mean or estimating these missing values.
If you're going to use
So one, oh yeah, go ahead.
if a model is going to use interpolation, is it better to use interpolation on a value that you know so that you know you have a realistic outcome. Like you test a bunch of data with complete or rows with complete data, and then you test your interpolation model against that to see if it comes out with the same or similar data that to the data that you know. Because you have a known, and then you test your case. If it doesn't come out anywhere near the known, then you know your model's garbage and you need to retweak.
Almost yes. And we're not even going to use the learning model that we create to do this data interpolation.
Mhm.
Instead, we're going to see in a little bit, we're going to use probably pandas and this other Python scientific computing library called scikit just to take our existing data and by using like looking at averages and standard deviations and trends, just predict, just calculate, a mathematically sensible possible value for these, right? And a simple example might just be maybe we get the average of everything, but we look at the standard deviation of these, right? If this is our norm, and we kind of have, let's say our data looks, I don't know, like this, and this is probably a terrible diagram because we have way too much stuff changing around the standard deviation, but we can just use some math to look at this difference, right? And let's say, for example, that I'm missing, and let me do this in maybe like green. Let's say I'm missing this bit right here. Can everyone kind of see this green circle that I'm drawing here? Well, we can relatively easily predict what that value might be, right? And I think you all can kind of just see that by looking at this graph. And so we can use like standard deviation and mean just to like calculate those values for interpolation. And Rachel, let me know if I'm like totally getting off course at any point with this stuff. So I have a decent but not a super strong understanding of this.
I think everything sounds good so far.
Awesome. And does
Does it
that make sense to folks? Oh yeah, go ahead.
it doesn't matter if you know if the variables were already scrubbed for outliers. No, I'm sorry, variables. The data was already scrubbed to outliers because like in this instance, water potability, if the null values here were already outliers and already removed, if you don't know that and you adjust the data again, does that affect your outcome?
Right. That is a great question. And that actually kind of takes us on to the next topic here. Let me go ahead and start doing a little TL drawing to tackle that. And I'm going to go ahead and save this Explorer tab for the moment, just to give us a little more real estate. Right. And so you're asking, hey, if I already know that like outliers were scrubbed from this data, do I have to, do I have to worry about it? Let me go over here to give us a little room to work with. And let's kind of just pull our funnel a bit further down. And let's talk about data preprocessing. And let's say that our data that we're working with looks something like this, right? Not an amazing diagram, but it's decent. It does the job. So short answer is I don't know 100%, but I'm pretty sure the answer to your question is even if our data has been scrubbed for outliers, the level of data consistency we need to train a learning model may be different than whatever reason the data was scrubbed for outliers for like a scientific study or something, right? Because maybe this data that we're looking at has already been scrubbed for outliers, but in order to train our learning model, And let's see if I can get this to draw a dotted line for me. If not, I'll just do it myself. Let's say maybe we have some tighter bounds that we need to fit our data into. Maybe it's because it needs to match with the other data when we're making tensors or the way the machine learning model works. Because, at the end of the day, we do need to end up with like a value between 0 and 1. So we may need our data to fit within a smaller range than for a scientific study or something. Again, I don't entirely know, but that's my guess, right? Because it always, depends who gets to decide what's an outlier and why, right? And so if this is maybe, I don't know, 0, I'm just making up numbers here. And so we've got like large chunks of our data that fall outside the range. And we need to drop them down to this. Because for the purposes of training our model, let's say, again, I made these numbers up 3, 0, -3. Just that 3 or -3 is our maximum value, right? And it might be 1 or -1. But the point is we've got data that's outside this range and we need to bring it back down.
Why would you want to
Does
do
that
that?
help answer your question?
That just feels like it's contaminating the data set with invalid data if you're shoehorning the outliers into the valid responses.
Well, so these aren't necessarily outliers. I mean,
If you're changing
there's
the data
different,
that was collected in order to get it to fit into the model, isn't that contaminating the data set?
not if we do it in a very consistent way, right? Because let's say I have 7.4 and 3.4 and 9.5. Or let's just make this 2.4. And I don't know, -6.7. So I guess one approach would be we could change like all of these values. Another approach might be, 7.4 becomes 3, 2.4 stays how it is, 9.5 stays how it is, and -6.7 becomes -3. But maybe like our model knows 3 is like max and -3 is min. So if we know like, hey, like 3 is the maximum positive value I can get, and -3 is the maximum minimum value I can get, it doesn't really matter if we have those values above 3 or -3. Again, I'm a little fuzzy on this, but another approach might be we shrink all the data in a consistent way to fit inside here, right? And then we don't have that issue of contamination at all because the difference between each value is really what matters for us. So some of this is a little context dependent, but to kind of go to this example, like just imagine we have a program that we say like if x greater than 3, return true, else, return false, or if x less than -3, return false. Again, this is kind of a made up example, but if this is our logic, we actually don't really care if our data goes beyond 3 or -3 for the purposes of what we're doing here. I'm not sure I could confidently speak on one strategy being better than the other. I think it probably depends. I think this strategy of scaling everything is a bit more intuitive because the relative distances stay the same. But we can see here two different approaches to fitting the data within the useful bounds for training our model. Does that
Okay.
help answer your question a bit?
It does. And also, I apologize. I tend to ask a lot of questions just for my own general curiosity. If it's not germane to the lesson, just tell me it's not, and we can move on, and you're not going to hurt my feelings. Like, if this is the way it
No,
is
I
done,
appreciate that.
then there's no point in me understanding why or why not.
Yeah, I probably need a little help being reminded to do that because I do love answering questions and digging into stuff. And as I said, I am a bit rusty on this. Um, but again, I think the main point here is we can imagine for some kind of program where like we don't care if we have values greater than 3 or -3. Um, and if our logic started to get fancy here, where it might cause problems, and we have different strategies for taking our data to fit it in the bounds that we care about. Yeah, I thought it was a great question, by the way. I'll try to do a little more digging afterwards to give a better answer to it, but hopefully this kind of answers it a little big picture.
Sure.
Yeah, me personally, I don't mind any questions you ask or anybody asks. I mean, it wasn't a factor that bothers me or anything. In fact, I mean, I like all the question asking.
Well, if anybody
Awesome.
else is annoyed
Yeah,
by it,
I
they can
do.
just tell me to shut up in the chat, and that's you're not going to hurt my feelings. It's pretty much impossible to do.
No, you're good. I think the more questions, the better. I just might need to be reminded to move on because I do love to dig into stuff. And in that vein, folks, feel free to remind me. Like, just be like, "Hey, Adam, let's move on, and we can cover this later." Um, but kind of moving on. This does touch on like different strategies we have for dealing with our data, um, and we just kind of discuss them. We've got scaling and we've got normalization. Scaling, I think, is usually called min-max scaling, where we scale data to a fixed range, typically between like 0 and 1. And in my example, I use -3 and 3. And 0 and 1 is probably a better example because remember, at the end of the day, we want our binary classifier to spit out a value between 0 and 1. So there we could see how keeping it to that range is useful. And then the other approach where you all saw me shrinking the whole graph relative to itself is more or less standardization, where we're centering data around our average, around our mean, with some unit of standard deviation. When we're talking about data, and this I'm going to get rid of, and in fact, let's just make this be 0, and let's just make this be 1 for consistency. When we're talking about our data, there's really two different kinds. There's the data points themselves, which are called attributes, such as pH and hardness and stuff like that. And then there's the actual correct output, and those are called labels. So we've got attributes such as pH, hardness, what was it, chloramine, if I'm spelling that right, and so on. And for each row of that data, for each row of attributes, we've got a label, which in this case is potability, right? And at the end of the day, we want to be able to feed in attributes to our model and get the correct label value to be spat out. So just to like kind of quickly step back, what we're going to do here is, I have my unprocessed data of attributes and labels and all that good stuff. And we are going to feed it in here to do our data pre-processing. And that's going to return, again, a bunch of data that has, and forgive me for moving stuff around here, attributes and labels and all that good stuff. And that's what we feed into our model, right? And in this diagram here, it's with pixels for a picture, but in what we're going to do in a second, it's with CSV data for water potability. So today what we're learning is we're going to see how to take this unprocessed data and perform some manipulations on it in a structured way, so we do maintain the kind of data integrity we need, and we get the data that is then ready to be fed into the model itself to train it and to evaluate how well it does. Great questions. Please do keep them coming. Do folks have any more questions before we start looking at some code?
So to get a little bit of clarification, everything we've been doing is not feeding the data yet. It's just cleaning up the data, certain values, missing values, closing off the range so it doesn't, in a sense, mess up. Correct?
Yeah, exactly. That's what we're going to focus on today. Correct. Yeah, good question. Because there's a lot of moving parts here. Because we've talked about a lot of the big picture stuff. We haven't yet gotten to the funnel itself. We will see tensors at the end of today's lecture. But today we're really focusing on these steps here, right? We're going to take our data and we're going to get rid of outliers. We're going to squeeze it into a range that's going to work for how the math of our machine learning model works, and tweak it to make it work better for training our model. And let's actually start going ahead and doing a little bit of this. So I can do this, and we'll kind of get this out of the way. And I think I'll just leave this off to the side here, just for us to kind of look at. So I can do this the hard way, right? If I want to work with a CSV file, I can import CSV. I can do with open and the path to the CSV file, which should be water potability.csv as file. Reader equals csv.reader. And I know I could use a dict reader or something like that, but this is just for a quick example. And if I don't have an error here, right, as long as my file path and everything is good, and if I type ls, I think it should be good. I should be able to run this code. And we get a ton of stuff printed out, right? This is, we have a lot of data here. If I want to calculate the average value of all of this and maybe reduce every single value here by some amount relative to the mean, relative to the average, that's going to be kind of tricky and kind of a pain to do with just plain old CSV manipulation. And that's where this library pandas comes in. And bear with me a moment as I get to my the right spot on my notes to look at this. There we go. So this is not really the way I want to do this. Instead, I'm going to use this library called pandas. And PyTorch actually uses pandas under the hood. And it's as you can see here, it's a Python data analysis library. And there's install instructions. This is actually a great video. There's a pandas cheat sheet that has a bunch of commands. I would highly recommend looking over the cheat sheet and watching this video today to see some more pandas stuff. Installation is pretty straightforward. We're just going to do pip install pandas. And I do already have my virtual environment activated that I have all my other AI stuff installed in. I know we had some hiccups here. I think everyone got it sorted. I would recommend use one virtual environment for the whole AI module, whichever one you got working last week. So it may or may not be in the same directory as your code. It might be easiest just to put all your Jupyter Notebook files like in subdirectories off of that root directory, or just all in that main directory. So I'm going to go ahead and install pandas. And let's see what we can do with pandas. I'm going to go ahead and import it and give it an alias. And with pandas, and let me go ahead and just get this thing. There we go. I can, instead of doing all that other work, I can just do data equals pd.read CSV. And I can give it the path to my CSV file. And if we output that data, and we give pandas a second to do its thing. And I'm not sure why it's taking the Jupyter Notebook so long, but there we go. So first of all, in the Jupyter Notebook, it outputs much more nicely. This pandas class is doing a lot under the hood. It uses something called a data frame, which is essentially columns and rows, and kind of lets us interact with this the same way we would with an SQL database that we'll learn about later. And just like Tensor gave us all these really powerful tools for working with matrices and with tensors, Pandas is going to with this CSV data. For one thing, if I just want to see all the data from one column, I can access it as if I was accessing a dictionary attribute. And now we just see all the hardness data from that hardness column. I can also use something called an iloc to give me everything in, say, column, or excuse me, row. To show row 35.
So what if we tried to do all this like on VS Code as opposed to Jupyter? Like, would it just be a lot more difficult to try to do all this?
Yeah, it won't really, I mean, and can everyone hear me okay, by the way? Okay, cool. For some reason, the speakers, it switched from my AirPods to the speakers, but as long as everyone can hear me, okay, then we're good. So you won't get nice output like this. You'd have to run the whole file, right? And you get stuff printing out and stuff like that. You know, I'd have to do, for one thing, I'd have to do print data iloc 35, and let's see what this looks like. It looks more or less the same. This just, it actually ends up being a lot easier because you can run this and get visual feedback right away. And also Jupyter Notebooks are sort of the standard way that this stuff is shared. Like if we hop back to the Kaggle page and we go here to code, what we see here is this water quality prediction model. This is actually a Jupyter Notebook that we're seeing kind of nicely displayed here. And when you download this, you don't get a Python file, you get a Jupyter Notebook file. So this is also sort of the language that the data science and machine learning community speaks in. Obviously, for like larger chunks of code, when we're like running it for production, it probably some of it does go in Python files, but for learning, for prototyping, for sharing, it's all sort of Jupyter notebooks. And like, nice tables like this are from Jupyter notebooks. Obviously, we couldn't get that in Python. This graph, they're in fact, they import some, I think it's called matplotlib, some Python graphing library to get this. But again, if I just ran Python from the command line, I wouldn't get this stuff printed out to the terminal, I don't think. So Jupyter Notebooks gives us these nice visualizations where we can run and modify our code and see the output all in one. Does that answer your question? Yeah, great question. So I strongly recommend using Jupyter Notebooks, even though I know it adds an extra step. The other reason is then you can talk about it on your resume, because this stuff is kind of like trendy and hot right now. And so putting on your resume, I built a learning model with PyTorch and Jupyter Notebooks, and having a Jupyter Notebook like on your GitHub is a plus. And by the way, let me just show you all real quick. Like if you hop over here in our curriculum repo, and let's just go to Zulu demos and notes. And if you want to peek ahead, you could look in, we could even look in Yankee demos and notes, because they have from the last cohort all these things that we taught. But if I open up a Jupyter Notebook file in GitHub, they do a really nice preview now where they actually execute the code in the notebook and print it out. Right? If I look at the code itself, oh, Lord knows what this is going to look like. So this is what the actual source code of a Jupyter Notebook file is, and no one looks at it that way because it would be, it's too difficult to manipulate, and it's not how you're meant to. So Jupyter Notebooks are definitely a win.
So to be clear, Jupyter Notebooks and PyTorch just work like VS Code. All of this you could do like on the command line, but it's just so much more convenient to visualize.
Yeah, good question. All the code we're writing in the notebook, you absolutely could run on the command line. You would not get these nice visualizations and this whole nice UI. All this stuff we're getting right now is with the Jupyter Notebook extension that we're running in VS Code, plus that Jupyter Notebook file that we installed, or package that we installed with pip. There's a bit more to it than that, but that's the essence of it. All the code, normal Python code, we can run it anywhere. Jupyter Notebooks and the VS Code Jupyter Notebook extension is what gives us the interactivity.
So is that long code on the GitHub page? Is that essentially just this whole VS code like compiled and then just put on into one big code, I guess?
It is this Jupyter Notebook file that think of it. In fact, what GitHub is doing here, you can actually run VS Code in the browser because it's actually written in JavaScript essentially. I hit the period symbol on my computer, by the way. So, right, I can actually see the markdown file without the nice formatting. But the same way that the GitHub, front end web app formats the markdown nicely for us to see, it does the same thing with the Jupyter Notebook. With the Jupyter Notebook file. If I hop over here, and let's just look at ours from a couple days ago. So I uploaded a bunch of stuff here from our last lesson, right? There's a TL draw file that won't render nicely, requirements txt, an image. And then over here, this .ipynb, this is the Jupyter Notebook file. Now, under the hood, it looks super. This is now GitHub essentially, it probably runs it in a server and then just spits the output here. But it's executing this Jupyter Notebook to give us exactly what we would see if we use the VS Code extension. I can't interact with it, right? The same way I can with the VS Code extension, but I see the output of this code being run and executed. The actual code itself for the Jupyter Notebook file looks like this. And it looks like it does indeed save like the output, but the output comes from running the code. And again, we would never actually modify a Jupyter Notebook file this way. Does that help answer your question? Yeah, great question. There's actually like a Jupyter Notebook server, and we installed that when we did pip install Jupyter. That's doing some of this under the hood. But yeah, this code, all this code will run just fine in Python. The Jupyter Notebook just gives us especially if we have graphs, right, and graphics, the nicer graphics and the interactivity and the markdown, right? The markdown cells in a Jupyter Notebook, like that's not Python code. Like if I go up here, that's not. This is not Python. That's Jupyter Notebook rendering our markdown for us. And I'm not sure how to edit it now, and that's fine. I don't need to. So yeah, Jupyter Notebooks, super cool. The VS Code extension gives us the interactivity. That .ipy and b file is the Jupyter Notebook itself. And all the Python code will run just fine outside of it, with the exception of anything maybe printing a graph. I'm not sure what would happen if you ran that on the command line. Does that make sense? And do folks have maybe other questions around Jupyter Notebooks? Cool. So this afternoon, really, we don't have like a straight up and down homework assignment. It's really going to be like code along with the Jupyter Notebook. And if you want the video up to get that hands-on experience typing out this code and running it, right? Because now is for learning and asking questions, and I'm not going to quite move at a code along pace. But in the afternoon, absolutely, you should go back and like that's how I learned this stuff. Is I literally pull up the Jupyter Notebooks from the previous cohort and I'll go through it line by line to kind of refresh myself. So this pandas library that we've installed, it lets us do nice things like print a row. It also lets us do nice stuff like slicing for a row. And I think we're almost due for a break. So let me just show this maybe, and that's a good stopping point. So this is going to give me rows 1 through 25. Right, and it looks like it doesn't include row 25 itself. It's row 25 exclusive. And this is really nice, right? Because I would have to write a bunch of Python code to do all this myself. And then the other really nice thing that this does to tie this back to data preprocessing is it gives us all of our rows and columns, but any column, any sort of cell, row column value that is null, it says true. But if there's a value, it says false. And in fact, if I want to maybe get this information in a more condensed and useful way, I can do data is null. And on that method, call this sum method that will add up for each column all the null values in it. And here I see the pH column has 491 nulls. These have 0. Sulfates have 782, and trihalomethanes, which is a tricky one to pronounce, has 162. So again, just getting rid of my null values is not a good idea because that will dramatically skew my data to just get rid of a bunch of pH settings. Plus, it will probably break code maybe when we're doing tensor manipulation, when we turn this all into matrices and tensors. So I'm going to need to either replace this with a mean or do some sort of interpolation to come up with a reasonable value for these nulls. So this is probably a good stopping point because we'll just kind of pick up here after the break. And then we'll start playing around with some of the statistical functions that Pandas gives us to create these values and add them in. Right, with the goal again of taking this unprocessed data and processing it in some form or fashion to fit the sort of numerical structure that we need to train our model effectively without losing the meaning of the data that we care about, which is really sort of like the relationships between the data points and over the range that we care about. Do folks have any questions before we take a break? All right.
Hey,
Why don't we
Adam,
Oh yeah, what's up?
that resource, the waterpotability.csv, is showing a file not found in the
Oh,
curriculum.
yes. Thank you for reminding me of that. I will update that in the curriculum, but to be honest, I think the easiest thing to do is just download it from this link here. And let me put that in the Zoom chat right now. Thank you so much for mentioning that, James. And let me put this I'll put it in Zulu questions as well. And I will add the link. I think I'll probably add the CSV file and the link to the main Kaggle thing, to the curriculum. So thank you. Thank you for mentioning that. And in fact, just so I don't forget, why don't I just put here, water potability CSV file, Kaggle. Right. And so here from this Kaggle page, I click on data card. And then if I go down here, the download button is this little arrow thing, and that'll download the CSV file for me. And I just moved it into the same directory as my Jupyter notebook. Yeah, good call, James. Thank you. Any other questions or things people might want to see again before we take a break? All right, let's take a break, and then we'll start seeing how we can actually handle these null data points. Thank you, everyone, and I'll see you all in 10 minutes on the hour. All right. So just to recap, we've talked about why data preprocessing is essential for our machine learning model. At the end of the day, our model gives us a value between 0 and 1, right? That's a prediction. And outliers like this will skew the effectiveness of our model to make a good prediction. And I don't want to have to handle kind of all these edge cases manually. What I want to do is, if I know that anything above a 1 means, this is negatively weighted, or anything, say, below a 0 is negatively weighted for water potability, I may just squeeze all of these values outside of our range to 0 or to 1, to our min and max. Another approach could be to scale the whole data set to fit inside, probably depending on the specifics of how we're training our model and what kind of data we're dealing with, right? And there's a number of mathematical ways to do this. And again, this is important because it makes the model have better predictions and be more efficient when training it. And we've seen that the two big things in data preprocessing are these outlier values, or values outside the useful range for us, and null values, because we need our data to be in a consistent format. And so this normalizing and scaling process will improve the training of our model and its performance. And we can either delete rows or columns with missing data. We can replace them with an average, or we can do some interpolation to estimate a missing value based on other data points. And then we saw how with the pandas library, it's really easy to, first of all, grab a CSV file, manipulate it, and then for our data preprocessing to find the null values, right? And we can get true or false for each cell sort of in our table if it's null or not. And we can get a summary. And we can see here that with so many nulls in pH and sulfite and trihalomethanes, that I probably don't want to just get rid of these values. I, in fact, want to do some sort of replacement or interpolation operation. And so that's what we're going to dig into more now is we have our sort of unprocessed data, but we are going to end up with some standardized data that then gets fed into the model itself. So let's keep on rolling with pandas. And I think where we left off here was I got a count of how many nulls there are in each column. What I can also do that's extremely useful in pandas is replace those with the mean value. I could do data dot fill NA. And in fact, let me show you all. So there's a data dot mean function in pandas, and that gives us the mean or the average for each column, for each attribute, right? Which is really handy. And I can actually fill in all those null values with that mean. If I do data dot fill NA, and my first argument, and we're going to impute missing values with the mean of each column. And my first argument is I'm going to tell pandas what value we're replacing the null value with, which is the mean. And because this is some sort of class, maybe a data frame class or something in pandas, it is smart and it will figure out, it will connect the mean for each column to the right spot. And I tell it if I want to replace in place, right, which will modify the data frame itself, or if I want to create a new data frame with those modified values. And let's go ahead and replace in place. And I'm going to go ahead and run this. And it doesn't output anything. But now if we do the same thing we did before of data is null sum, we should get nothing, because all those empty values have been replaced with the average or the mean value for each column. So we can see Pandas lets us really easily replace those values. And do folks have any questions about sort of that replacement imputation operation that we just did with Pandas?
I don't have a question about that. Could you scroll up to where you actually declared the data variable in Pandas? I lost that code somehow.
Yeah, absolutely. And I'll post all this to our demos and notes repo as well after the lesson. It's way up here, but it's super straightforward. It's pandas.read or pd.read CSV, and then I just give it the file name.
Thank you.
Yeah, totally. Okay, so this is cool because we don't have any null values now. Now we do want to do some scaling and normalization to reduce the values of data that are out of range and do it in a way that like preserves relationships between these values, so it won't mess with our training model, and it'll in fact help it train better. We can do this. We have to use a different library called scikit-learn to do this. And we can go ahead and just import it like this. And from this library called preprocessing, import standard scalar. And anyone tell me why I'm getting these red squigglies? Or orange squigglies?
You don't have it imported?
Yeah, exactly. I haven't imported it yet. So let's take a quick look. This is an extremely popular library for, as it says, machine learning in Python, and probably other scientific computing and data science and number crunching stuff in Python. Python is used for a ton of scientific computing. That's why it became sort of the language of machine learning. PyTorch uses this under the hood as well. We're going to go ahead and install this. And for those of you on Windows, remember you're using WSL2, so you'll use the Linux install step. And again, don't worry too much about coding along now. And the commands are basically the same. It's pip install -u with a capital U, scikit-learn. And we'll give it just a moment to install. Depends on some other things that it's installing. It's pretty nifty. Examples, I think, are always a good place to go to. The user guide sometimes has a tutorial, though I'm not really seeing a tutorial off the bat here. They might have it hiding somewhere. But so I've got scikit installed. I might as well run these commands that it tells me to make sure I have it installed correctly. Python-m pip show scikit-learn. And it prints out a whole bunch of stuff, which tells me that scikit-learn is indeed installed. The next command is just for making a requirements.txt file, but that's not the worst idea. So I'm going to go ahead and just do that right now. And over here, I'm just going to trust that it's picking up correctly from my virtual environment because it has been, and let's go ahead and use it to do some stuff. So there's different kinds of data, right? We've talked about this distinction between attributes and labels, where attributes are pH level and hardness, and so on. And the label is potability, the value that we want to end up with. You'll also hear this term features used for attributes and target for the label. And right now, I don't want to mess with my label data telling me, hey, this water is or isn't potable. I believe this is already sort of on a scale between 0 and 1. In fact, if I just do data potability, we can see what our potability data looks like. And it looks like it's taking Jupyter Notebook a minute here. I'm a bit surprised it's taking it this long. I wonder if it's because it's importing standard scalar. It's because I probably did something wrong here. And in fact, I'm missing the D in standard. So there we go. We see our potability data. We could check manually to see if there's like intermediate decimal values here between 0 and 1. But the main thing is we can kind of like guess from this that we're mostly looking at zeros and ones, right? So I don't need to fit this data. So over here, when we're working with our standardized data, we're actually not going to worry about the potability, the label, the target. I want to focus on the attributes or the features. So I want to just grab that attribute data. I want to be able to really separate my features from my target, right? My attributes from my labels, my raw data I feed into the model from the potability number that tells me if this water is potable or not. So I can do data.drop and tell it to drop the potability column. And we might as well grab it as its own value because we'll want to use it later. But now features has pH levels and all those good things, but no potability, which is exactly what I want here. So now I do want to do some sort of standardization on this. And the way I do this with scikit-learn is I create an instance of this class called standard scalar. If we kind of hover over this in VS Code, we can get a brief description of what this does. It standardizes features by removing the mean and scaling to a unit variance. And then it goes into a bit more math. So in essence, it's removing the average value from everything so we can see the difference from the average and then doing some sort of scaling operation. So everything is fitted nicely on a graph, probably by a standard deviation. And I can use this by calling a function called fit transform. And this isn't the greatest description. I was playing around with ChatGPT earlier. I thought it did a very good job kind of describing what this does. And it's doing two different things, right? It's fitting something to our data and then transforming our data. So I'm not sure about the model part, to be totally honest. But what it is doing here that's important is calculating the mean and the standard deviation from the mean for each of our data points. And then it is going to modify the data. And we're not really passing in any values here. So right now, it's just subtracting that mean, right? So if everything in our data has an average of, let me go ahead and draw this. Bear with me one sec to pull up the annotator. You know, if this is our data and I don't know, this is our mean and this is, let's just say this is 0. It's in essence getting rid of all this and scrunching it down and then multiplying by some standard deviation from the mean. And that is probably not the best diagram, but I don't want to get too lost in the sauce because I'll probably end up explaining exactly what it's doing incorrectly. But we can see it's doing these two operations that essentially scale the data based on the mean and standard deviations from the mean. And if we go ahead and we look at this scaled features data, and let's go ahead and just print them both out, we can kind of look at a bit of the difference. I think it's probably actually a bit hard to see it this way. This is our normal features data. So there's values like 7, 3, 8, 9, 204, 129, so on and so forth. And then if we go to our scaled features, first of all, what kind of data structure does it look like this is in now?
A
It's a
list
little
or an
hard to,
array.
sorry?
A list or an array.
Yeah, and it's a little hard to see, I think, on the screen share, but it's really an array of arrays. So it's a matrix, or it's probably, in fact, a tensor. And we can see now, like, all these values look dramatically different. They're all being raised to this power e, which is, I want to say the square root of -2, by some certain power. So they've all been scrunched. So in some form or fashion, we now indeed have taken our data, and we haven't done it exactly this way, but we've scrunched it in to the range that we care about.
Before you had just printed out the scaled features, you had features above that. Why did you use print features instead of just features?
Because I think what Jupyter Notebook is doing here is whatever the last variable is, it will print that out. So if I just do this, I'm actually not sure if it will print both out, but my assumption has been no.
No, it won't.
Yeah, yeah,
But
because
but
yeah. So I just wanted us to be able to see both together, if that makes sense.
oh, okay. Because they're different commands.
Yeah, they're different variables, exactly.
Makes sense. Thank you.
Yeah, for sure. Good question. Um, and you know, I would love, in fact, to graph this. Quick way to graph scikit learn bit transform output in Jupyter Notebook. Yeah, I'm not going to try this right now. It's very tempting, but I think I would get lost in the sauce. But we could, in fact, make a graph of this, and it would be kind of cool to see the difference between the scaled and the non-scaled data. But that's a little out of scope for right now, unfortunately. So now that I've got this data scaled, I do want to break it up because I kind of need different groups of it. Because we've got this standardized data, right? Attributes and features. But I need some testing data and I need some evaluation data. Because if you all think about, if you take a quiz, at school here or wherever, and you have some practice quizzes beforehand, if the actual quiz has the same problems, the same questions as the practice quizzes, that's not a very good way to learn, and you would just end up memorizing stuff. And the same is true with training a model, where I in fact need some data for training and some other data to evaluate how well the model has been trained. So some of my standardized data needs to be evaluation data. And in fact, I think the proportion that is sort of like the standard for machine learning is like I want to say 80%, 20%. And then I need a bunch of my data to be training data. Yeah. And I think sort of the standard starting point is you want like 80% of your data to be training data, and you save 20% of it for evaluation. And does that make sense what the different purposes of these two data sets are? Awesome. And I'm probably going to want to just have different groups just so I can be running my training multiple times. And so I might want different testing groups and training groups and different evaluation groups as well. So let me go ahead and print this whole thing down. My apologies. I'm not going to mess too much with the diagram because I'll get lost in the sauce. But let's just go ahead and actually run some of this code so we can see how we can grab this training data. And the good news is that it actually makes this really easy. I do need to import some more methods from the scikit-learn. And we're going to import a function called train test split, which does something very similar to what it sounds like. It's going to return a tuple. And we're going to get one set of training data, train test data, and then like another group of training and testing data. And I believe what this also does is randomize this for us because I want to make sure that my data is randomized, that I don't have like a huge chunk of similar data for training or for evaluation, because that could skew the model. Like if the practice test had all geometry questions, but then the actual test had all algebra questions. I need like a random mix of all the different kinds of questions. And so I'm not going to use the parentheses for the tuple declaration because I can do this style. And let me make sure I'm getting my names right here. And so train test split is going to return a tuple that then gets assigned to all these things. And it looks like I have some sort of typo because I'm missing a comma. And we need to pass in our standardized feature data. Let me make sure I have that variable named right. It should be scaled features. And I'm actually going to now pass in my targets as well from before.
Can I just make one comment?
Please.
For the for the training B and the testing B, those last two are actually your targets. So you would train on A, and then with the model you make with A, you would use like your training Y to say like if that's a good model.
Oh, I got it wrong. Got it. Thank you. And in fact, if we hover over here, we can see the list that it returns if I scroll down a bit. List containing train test split. Oh, could you say that again? What did
Yes.
what?
So with your training and testing, like if you go back to your diagram, technically you're in your TL draw under the training data, you have the attributes and features, but you also need the target. So like if you made a basic linear regression model, you would use your features to estimate your target Y. So you need to pass in both. And then when you evaluate, you still have like your answer to compare it to. So for the probability, in order to see like how good your model is actually, you also have to train it with the target. Does that
Got
make
it.
sense?
Yes. Yeah. So I think I see what you're saying. So then would this here be target, or you're saying it should be kind of inside this part here as well?
So no, I'm just saying like you already split up your data above into features and target. So when you do a train test split, you're just splitting up you're still splitting up your features. So you split up your features into 80/20, but then you also split up your target into 80/20. I don't know if
Got
that
it.
makes sense.
Nope. That makes perfect sense. I see what you're saying now. Um, in fact, let's just make the target blue. Um, because you're saying, hey, when we feed the training data into the model, it needs some target information as part of the training process.
Yes. And then when you evaluate your model, you'll create like with the model, you'll create like one thing of input, but then in order to compare how good your model accuracy is, you'll use like your model, you can call it like model creation output, compare that to your test output, and then you can see how accurate you did.
Got it. Thank you so much for pointing that out. And what does it use in the training process? How does it use the target data again? You were saying something about like a linear regression.
I feel like that's like the easiest example of a model. So I was just trying to say, like, if you're making a linear regression model, like normally an example would be like height and weight to get your BMI. You use those two variables to estimate your BMI. Your BMI would be the target.
Got
It's
it.
just like your features are normally X1, X2, X3, whatever, and then in like mathematical terms, your target's a Y.
Got it. Got it. Thank you. Okay. Yeah. So I totally. Yep. No, that makes so much sense. Yeah. So I totally grouped here. I suppose we could kind of add in like sort of an extra step where like before we break up our data into training and evaluation data, we have the standardized attributes and features. And then when we break it up, we need to add our target data back in. Um, yeah, Rachel, thank you so much for pointing that out.
You're muted.
Oh, man, sorry guys. When did I get muted there?
I last heard you say thank you.
Yeah, got it. Thank you. Yeah, thank you, Jack. I was saying, I was just going to look at the train test split function to make sure I have it right, where we're passing in these scaled features. We pass in our target data, which is the potability data that we haven't done any scaling with. Um, and then I think what this is doing is it says maybe how big each test is. I'm honestly not sure what test size is doing there. Um, It's the proportion of the data to include in the test split. Got it. So this should actually, I have a typo here because we want this to be our 20% of data. So this is our evaluation data there as 0.2. And then we add some randomness, and let's see what that random state argument is doing. Right? So this function will also, just like shuffling a deck of cards, do some sort of randomness operation. And it looks like we can control the degree of randomness, which I think is a direct equivalent to, how many times do I shuffle the deck? And for consistency, we can pass in a number. So in essence, we're shuffling the deck 42 times. And there's a shuffle Boolean argument as well, but I'm not going to worry about that one at the moment. And then this should return us training data and testing data for group A and training data and testing data for group B. And let's just test this out real quick by just printing out some of these things to make sure that these look sane and that the code executes. And let me bring that code block back. And so we see here some tensors. In fact, here we get the shape of our tensor printed out. And if we look at the testing data, mainly I want to see that it's smaller. And I believe this is a smaller group. And we might as well just print out testing B just to make sure that I've got all this correct. And this looks like our potability data here. And what is training B? So it looks like I have a mistake here, actually. Though I'm a bit confused from looking at the docs for the code. And I think you were saying this before too, Rachel, that both of these are the training data tensors and these are the testing ones. So let's just quickly look at the actual docs for this. If I hop over to scikit-learn and we go to the API, let's find train test split. And let's take a look and see what it says. So it returns a list of our train test split of inputs. And here is, in fact, the same thing that we're doing here. So I think this should be okay, but it does seem like it sure does seem like testing A and testing B look like different things.
Can you print your training B to see what that looks like?
Yeah, totally. And it looks very similar to both the B's look like this. So I feel like I've done something wrong here. Um,
You can compare like the lengths of it does look like different than what the documentation's telling you. It kind of looks like it's giving you train A, train B, then test A,
Yeah,
test B.
yeah,
So you could just compare the lengths of one should be 80% of the length of the full data set and the other one should be 20%.
yeah. That's a good idea. Let's do print. Man, training a. Let's see if I have that right. And I think it's a property. And now if I do testing a dot size, yep, I think you're right. And if we do print scaled features dot size, yep, it sure does look like testing a is well, that actually seems right because that is roughly 20%, right? If the total amount of stuff is 2,900, or 29,000 rather, 80% is 23,000, 20% is 5,900. Um, I wonder if I have a problem. Scaled features seems like it
Wait,
was
no,
fine.
sorry, I think I got it. It's because your training A and your testing A should both be the features, and then your training B and your testing B should both be the target. So then when you make your training model, you're using your training A and your training B, not training A and testing A. Does that make sense? Because you want to make
Yeah,
a train model and then a test model.
yep, yep. That I think that does make sense. That this is the training data for our test. This is the training data to train the model, and then this is our evaluation data. And then this is our target data for training, and this is our target data for testing. If I'm
Yes.
tracking what you're saying, yeah,
Yes. So
yeah,
everything does look good actually. It's just like the
yeah,
A and B when I'm used to X and Y was like
yeah.
a little
And I
confusing.
think these names are just not good. I think if I'm going to go back to this, let's call this. Um, so this is our training data. So let's call this training features, and then let's call this evaluation features, and let's call this training targets and evaluation targets. Does that sound right to you, Rachel?
Yes.
Yeah, I think so. And now if I do training features, and we can get rid of that and we can get rid of that. And if we run this, we'll see what looks like our feature data. And if I do evaluation features, I'll see what looks like feature data. And if we do the size of all of our feature data and the size of evaluation features and the size of training features. Yeah. So this just, I mean, I got a little lost in the sauce here, but it only goes to show I think this stuff can be confusing for everyone. And there's a saying that the hardest task in programming is naming stuff. And this is a good example of it. The code was actually correct. My assumption about what the code was doing and which part was what was wrong, in part because I chose some, I think, not very, or at least variable naming conventions that I wasn't used to. Um, so hopefully this was like good to see a little debugging in practice, if nothing else. And also now we have some much clearer names. And if there's one lesson to take away here, it's the value of like consistent names for things. Like we're calling this training data and attributes and target or features. Then, we call this training features, evaluation features, training targets, evaluation targets. And Rachel, thank you so much for helping me debug this. How are folks doing? Because I know there was a little bit of debugging there, and that can be a bit like tiring over Zoom. How are we feeling?
I think personally, like the coding stuff makes sense, but dealing with like the whole data analysis part is just something that probably most of us have no any level of experience with. And so that's just like a lot for me personally. It's just like trying to understand like all the different targets and all this other stuff.
Yeah, I
Yeah,
think that totally makes sense.
I mean,
Oh
me,
yeah, go
me
ahead.
personally, I think I need the hands-on because I just feel like, I mean, I would get more out of it if I was doing more hands-on with this than just watching it.
Totally.
I
And I think
think,
to be honest, oh yeah, go ahead.
sorry, I was gonna say, are we still just basically going through the different methods within inside of Panda, and that's what we're importing?
Panda and now scikit-learn.
And
Yes.
scikit-learn. Okay.
Yeah. So what we're seeing here is sort of the key step that you'll want to run once we get to like working with data and building models. And I think this afternoon, really, I think the homework is basically just go back through this and code along to get your hands on it. And the good news is, I don't think we'll have to do a massive amount of tweaking of these values here, right, in this function that I'm calling. I'm moving this down onto a separate line just for readability, because this is a lot of words. I think the main takeaway to kind of just recap the most important stuff is we want to use this fit transform function on our data to scale it. And I think, though this is not a perfect example of what scaling is doing, we can think of scaling as effectively doing something like that to fit the data within the range by changing it all proportionally. Before that, we need to get rid of our nulls. And again, this code, you can pretty much, I think you can pretty much use this directly. So certainly kind of for tomorrow, I don't think you all will have to be massively tweaking this. And then here, there is a lot of stuff going on. But just to recap, what we've done is we've taken this data, now that we've standardized it by getting rid of nulls and by scaling it to fit within our range, and we've chunked it up into two groups, right? We've randomized it, we've chunked it into two groups, and we added back in our target, the potability values. And we do that with this train test split command right here. And again, this command itself, like, I don't think you'll really need to be tweaking test size or random state that much, at least to get going, right? I got a little lost in the sauce with what this is returning, but once you have these values, I think you're fairly good to go. It sounds like, am I correct in thinking that kind of maybe where folks are struggling with is like the understanding what the scaling does, or is it more of just like all of the numbers and the different functions?
Yeah, it's more so like all the numbers of the different functions.
Yeah, no, that totally makes sense. And then I had to do a little debugging there as well. Let me take this home because our final step here is going to be to make some tensors. And then we can do a quick review to just sort of see everything we've done from top to bottom. And I think that'll help. Sound good? All right, let's do it. So now that I've got my data and I've got it named in a way that I can remember, I actually want to turn it into tensors. And so, oops, sorry. Let's make a code block here. And let me give us some room to look at this. So I've got training features, right? And this is pH level, all the different data points that we're going to train our model on to see if water is potable or not. And I'm just going to call this training features tensor. And we're going to use torch.tensor that we saw the other day to convert this into a tensor. And we're going to have it convert all of the data to a floating point type, which is to say to give us decimal values, like say 3.5, a 32-bit floating point. And if I go ahead and print this out and run this, then we can see now I have one chunk of my data as a tensor, right? And that is this bit over here. And now let's do the same thing for our training target data. And again, we're going to make the data type 32-bit floating point. And let's make sure that that runs. And it looks like I have a typo. And it looks like
Do you need the 32 at the end of your float?
I do need 32 at the end of my float. There may, in fact, be an additional issue here that we have to tackle, though. Yeah, so we will come back to that in a sec, because that actually raises an issue that we have. And let's take instead our evaluation feature data. And we can see that that prints out. And let's talk about the issue that we had with the potability data, with the target, right? Because to kind of zoom in here and look at what this data represents. Over here, I've got, some sort of matrix of matrices, and it looks something like this, like 0.4, negative 3.2, 4.5, 0.3, whatever. And this is pH levels and chlorine levels and water hardness and whatever all of those other attributes or features of the input data is. Right? And it's the same thing over here. We just have less of it. But then over here, our target data just looks like this. 0.4, 1, 0, 0.3. And I've got two tensors with different shapes, right? This is, in fact, I think, what maybe a zero-dimensional tensor. It's just a list. So I think I have to do a little work to turn this into a matrix, a list of lists, right? And let's go ahead and do that now. Because it can't just be a list. So my training target data tensor going to do torch, tensor, and training target dot values, and I'm going to set the data type to the same thing of float 32. But then I'm going to use the view that we saw the other day so that we're getting these values and putting them into a tensor. And if I got this right, let's see what we get. Right. And so now my data looks like this, right? Where each value, and let me just give a little more room here so we can see this better. So we have a nested list. Y'all see what I'm saying here? Which is what we need so that we can have a tensor. Because now I can manipulate these the same way I manipulate these. And that's really our final data transformation step. And we're going to do the same thing for our evaluation target tensor as well. And that was the error that we were seeing before. I had a typo with the floating point error, but also we needed to grab these values so we could return a tensor and turn it into a tensor because it was just a list before. So that's really the final thing here. We've covered a whole lot of ground. Let's kind of step back and just review it from the top. And then we'll, in fact, be wrapping up right on time. So we started off with a whole bunch of CSV data. And we very quickly decided that we don't want to use the built-in Python CSV tools to manipulate our CSV data. And we have this unprocessed data with these attributes or features. And then we have the actual value that we care about, that we want our model to spit out at the end of the day, a number between 0 and 1 that's a prediction of how drinkable the water is. That's called the label or the target. And so the first thing we have to do is with the attributes and the feature data is we have to get rid of null values. And so I read my CSV file into pandas with this pandas.readCSV command. So we can manipulate it. And we played around with that. But then most importantly, we used isNull.sum to see how many null values we were dealing with. And there's 3 things we can do with null values. We get rid of them, we replace them with the mean, or we do some sort of interpolation to come up with a realistic value for it, right? To fill in the curve. And we decided just to replace it with the mean. And again, we can do that in one line here with pandas, where we use this fill null command, essentially. And we tell it, replace every null value with the mean and do it in place to modify this actual pandas data frame instead of returning a new one. Once we've gotten rid of our null values, we then do want to scale this based on standard deviation from the mean value so that, in essence, the values of our attributes are within a useful range for training our model. So our model doesn't have to deal with tons of edge cases, or we don't have to write code for edge cases. So the data is more structured and it can come up with better predictions. And then it can really handle other edge cases on its own once it's been trained with good data. So the next step to do that is using scikit-learn. We use this standard scalar class and this fit transform function that, in essence, shrinks everything down relative to the mean and scales it relative to standard deviation. And then we now have all of our feature data, the pH levels and everything like that, that's been scaled, which we have right over here. And this is about, 75% of the work. And then our final step was, well, some of this feature data I need for training. Some of it I need for the final exam to see how well my model has been trained. So I need to randomize this and take 80% of it for training and 20% of it for evaluation. But Rachel, like you reminded me of and correctly pointed out where I got wrong is when we're training the model, we also need this potability data to help the model refine itself, our target data. And I need that both for training and evaluation. So I need to grab 80% of it here, 20% of it here, and of course, randomize it as well. So over here, we use this train test split function. And let me bring these back on one line. This is a monster line, I know. And it returns a tuple with a whole bunch of values. But it gives us a tensor in essence, or a nested list of our feature data that's been scaled and standardized, our feature data for evaluating, our feature data for training, and also our targets for training and for evaluation. And this was me sort of debugging the code. And then our final step is to turn all of this into tensors. And when we do that, because our target data is just a plain old list, I need to add an extra list to wrap around it, which we do with this view command right here. So we can turn it into a tensor. So, it was a long journey to get here, but when we step through all of this, we've got probably about 20 lines of code, maybe, where, there's a lot of numbers we plug in, but there's not a huge amount of variability we need to do right now. Like, this is a pretty, I think, safe standard approach. Does that walkthrough help kind of break down the steps of how to do this a bit and to see how each piece connects to the next? Or does it still feel like I just kind of need to get my hands on this?
Yeah, need to get my hands on. So
Yeah, I would say it helped a little bit, but I would still need to get my hands on more than likely.
Yeah, totally. And I think that's really what this afternoon is for. Let me go ahead and stop the recording, and then we can talk about the rest of the day.